Hello and good evening, and welcome to the IRDR monthly seminar. Really pleased that you can join us today, and we've got a presentation both by Professor Bernd Kulessa and Dr. Chloe Gustafson, who are doing a dual presentation, actually from different continents, but we're hoping that's all going to sync together. They are respectively Professor and Postdoctoral Researcher in Geophysics and Glaciology at Swansea University. Their research aims to improve our understanding of the future dynamic contribution of the world's ice sheets and glaciers to sea level rise through geophysical exploration. And more broadly, Bernd has interest also in magnetotelluric imaging of the Earth and the applications of geophysical techniques to assess and characterize ground hazards and contamination. He's been principal investigator on many grants for research into the dynamics of the Antarctic and Greenland ice sheets. Particularly noticeable discoveries include the spatial prevalence and hydromechanical diversity of sediments beneath the Greenland ice sheet, seismic imaging of hydrological triggered fracture through ice sheets, which then modulates sediment strengths and ice sheet flows, and the fundamental controls that internal heterogeneities exert on the stability of Antarctic ice shelves. So with that introduction, I will hand over to Bernd, if you would like to go ahead, please. Thank you.
Okay, thank you, Peter, and I'll try and see whether I can share my screen. Okay, there we are. I'll just get this started. Yeah, so welcome everybody, and thank you very much to Peter for the kind invitation for us to give this presentation. Yeah, as Peter said, I'm a professor at Swansea University in Geophysics and Glaciology, so I've done this for like around about 25 years now. Have done quite a lot of things in my life, especially on the ice sheets. And Chloe Gustafson, as she will say, she's just finished her PhD at Le Mont Doherty Earth Observatory. So it's just started yesterday, actually, as it were, as a postdoc at Swansea University. So it's a formal welcome to her. She's done some fantastic work doing a PhD on the Cyprus coast in West Antarctica. And she's going to show us some examples of the most exciting findings that she's produced from it so far. So the idea is that I will give you a general introduction, and I will particularly focus on, what is this subglacial groundwater idea all about? So why should we care about it? And why does magnetotelluric geophysics help here in particular? So Chloe will explain to you what magnetotelluric geophysics actually is and why it might be particularly useful. I will also say a few words. And at that point, so Chloe will take over and show her some of the exciting work that she's done. And then I will finish off again at the end, wrapping up. And we'll also say a few words about geothermal heat flux underneath the Antarctic ice sheet, because we know very, very little about these things, like neither how water affects the ice flow. We don't understand that very well. And one of the biggest unknown in ice sheet science is, what is the geothermal heat flux? How much heat comes from the inside of the Earth to the underside of the ice sheets, and how does that affect the warmth at the base of the ice and how the ice basically flows? And this is pretty much, what I really am feeling very passionate about investigating in the next 2 years. So if we just look at the big picture first, so this is just aside from ice sheets, I guess. So there was a big inventory of groundwater on the Earth. So here's, without going into detail, but you can see a picture here. The darker the colors, the more groundwater. The lighter the colors, the less groundwater there is. And what you can quite clearly see, and I'm going to try and see whether I can switch my pointer on here so I can use that a little bit. You can see, we're basically sort of mid-latitudes mostly where the groundwater has been mapped. We know virtually nothing at all about what groundwater does in the northern high latitudes, and Antarctica doesn't even appear on this map. So we clearly got a really big problem there. So we need to figure out what's going on with that. And this is pretty much what we're hoping to do going forward. So for contemporary ice sheets and glaciers, we fundamentally don't know whether there's groundwater underneath them, and if there is, what effect that might actually have on the ice flow. And to this extent, I said Chloe's already been lucky to be able to make some useful measurements during her PhD, but we also have two NERC NSF funded projects in West Antarctica in the next sort of between now and 2027, actually, for the Institute Ice Stream in West Antarctica and Thwaites Glacier also in West Antarctica. And I'll show you a map in a little bit that basically shows where those places are. So we're going to have a lot of opportunity to do field work in order to, figure basically out what Chloe and I are going to present to you today. So let's start in Iceland. So what you can see, there's a sort of light blue color there. And this is just to point out that actually we're not really reinventing the wheel here, but there has been quite a bit of thinking by clever people in the past, including my colleague Gwen Flowers, who's at Simon Fraser University in Canada, in Vancouver. So she's previously done combined ice dynamic modeling and hydrological modeling, including groundwater in Iceland. And she's basically tried to figure out what happens as the climate warms in the Arctic. It sort of warms above average in the Arctic. So we can expect to see, although, okay, Iceland isn't quite in the Arctic, but it's not far off. But it'll get pretty warm there over the next 200 years. The ice caps will retreat quite a lot. And this will have quite a substantial impact on both the surface water patterns of flow that you can see on the left, as well as the groundwater flow patterns on the right. And that will have quite severe impacts on river basin flow. So I won't go into detail here. This is just to sort of set the scene a little bit. And in fact, if we look at the paleo ice sheet literature, then it turns out that the reason people really started thinking about the groundwater effect with ice sheets is because there's been a lot of work in the sort of Great Plains aquifer system in the US for many years for groundwater prospection, but also oil hydrocarbon prospection and so forth. And they've realized there was something really fishy going on with the groundwater flow patterns in those big sedimentary basins. That didn't make any sense until they started realizing actually this has something to do with the fact that the Laurentide ice sheet actually used to sit over those big sedimentary basins and actually wreaked a bit of havoc in those places. So in the Pleistocene, for example, when we last had a growing ice sheet, this is sort of roughly the situation that you can imagine. So here's basically a transect from sort of South Dakota through North Dakota and up into Manitoba in Canada through the Williston Sedimentary Basin, which is around about 4.6 kilometers thick in the middle. So we're talking about quite a lot of sedimentary rock here. And when the Laurentide ice sheet was growing, it basically started overrunning the basin. We might have had a subglacial lake forming, for example. But the net effect is that basically the groundwater flow patterns from underneath the ice sheet are basically in this manner, that the water gets pushed outwards along the aquifer units, which are here shown basically in white with confining units, aquitards in between them. And so the water flows away from the ice sheet. But then in the modern times, so both Greenland and Antarctica, Iceland, other Canada ice caps are shrinking at the moment. And so the situation we have, okay, here's the extreme situation where the ice has actually disappeared. But if we have an intermediate stage like we have in Antarctica and Greenland, for example, we still have a situation where those groundwater flow patterns will actually start reversing and the water will start flowing back to where it came from originally. And so we have a situation, for example, where we know there's hundreds of subglacial lakes beneath the Antarctic ice sheet that we have already detected. We'll keep finding more of those in Greenland now as well. And the idea is that, as you will see in my next slide, is that those sort of discrete water bodies like lakes, but also channels of water flow underneath the ice sheets can be potentially the connecting points between the base of the ice and the deeper sedimentary basins that are sitting underneath. And this is kind of conceptualized here in my next slide. Again, you can see ice sheet advanced in the Pleistocene. We have a lot of meltwater being produced. The hydraulic head is very large. We have subglacial channels, which are basically these giant rivers that flow underneath the ice sheet here. We have a till layer. So these are basically unconsolidated sloppy sediments between the ice above. Then there's a sloppy sediment layer that actually allows the ice to flow fast because it's really slippery. So it deforms the water pressure in it is very high. So it's a bit like a slipping in the bath effect. So the ice can actually slip over this slippery till layer. And then we have the sedimentary basins basically underneath it. But in an advancing ice sheet situation, we have got very high hydraulic heads, so the water gets pushed out of these subglacial channels or subglacial lake if they basically grow into big lakes out into the sedimentary basin itself. And then when the ice sheet retreats, like we have in the current situation, for example, the water pressure changes. So the channels themselves then tend to have a low hydraulic head, which then means they will start attracting water flow back into them and then start evacuating the water sort of downstream, somewhere downstream on the ice sheet itself. And that will become important in a second because not quite this slide, but I think the one afterwards, it's going to basically try and make the argument now that we have ideal situation in Antarctica, for example, for groundwater to actually make a really important contribution to the subglacial hydrological system, or the amount of water that sits at the till layer, lubricates the till layer, and therefore allows the ice to slip really fast. So for example, here from Stuart Jamieson in 2010, he's reconstructed where there's a lot of basal erosion of sedimentary rock going on. So the redder the colors, the more erosion of the sediment there will be. So the more sedimentary rock will build up, and also the more till will be available to deform and therefore to allow the ice to flow fast if you also have enough water in those situations. And you can see there's a lot of big outlet glaciers, a lot of situations here in West Antarctica, but all around Antarctica really, where we have a lot of erosion going on, where potentially, we have a lot of very thick sediments and till building up. Yeah, so the 4 places we're going to touch upon in this talk is the Cyprus coast. So this is what Chloe's going to show you. She's done some measurements down here. I'll say a few words about the Institute Möller ice stream in a little bit. I'll also say about Pine Island Glacier and Thwaites Glacier, which are on the Amundsen coast, which is over here. Also in West Antarctica, and then in East Antarctica, there are also some big sedimentary basins sitting in the middle here, which have built up over geological timescales. There's not so much erosion going on right now, but in the past, there has been a lot of erosions here, and there's some big sedimentary basins in this area there. So those are sort of roughly the areas that we're going to mention in this talk. Stephen Livingston in 2013 and others since then have basically done a lot of modeling in Antarctica and used a lot of airborne radar data, for example, and have realized that we probably have a very active hydrological system actually being present underneath the Antarctic ice sheet, where we have big rivers, those big channels that I showed you conceptually in my earlier slide, but we also have a lot of subglacial lakes, which are all these blue dots that you can see here, and some of the yellow dots, which are basically reconstructed by this hydrological mapping. So there's some subtle detail in here that I won't go into. The key message is that we basically have all the ingredients that we need for groundwater to play a role in affecting ice flow, because we've got lots of sediments, lots of till, and we also have lots of water, and those are basically the things that we need. So the question then is, so is the flow of the Antarctic ice sheet basically affected by water that was built up when the ice sheet was advancing? So is there any contemporary evidence at the moment to say that groundwater might be playing a role? And there's 2 key studies that are probably worth flagging up at this point. One is from Paul Gustafson, who did a hydrological budget of the Cyprus coast ice streams. And he realized that there was around about 47% of water at the base of the ice there comes from inflow from the ice sheet interior. So that's water that comes through those big channels from somewhere interior of the ice sheet and then flows downstream towards the ocean through those big channels and underneath the ice streams, basically that are sort of transporting the ice from the continent into the ocean itself via the ice shelves, which are the floating parts of the Antarctic ice sheet. And then around about 8% on average came from local basal melting due to geothermal heat flux in that area. But then he realized there was 45% of water actually missing. And the only way to reconcile this is by allowing groundwater to basically seep upwards and basically lubricate the till layer underneath those fast flowing ice streams that are transporting ice from the ice sheet interior into the ocean. So that was a key bit of evidence. The second key bit came from those East Antarctic sedimentary basins that I showed you a little while ago in one of my previous slides, where Brad Gooch et al. Did some modeling, where they initially had a growing ice sheet, where we had a negative volume flux of groundwater. So again, don't worry too much about this. So the different colors mean permeability. So in pink, we have low permeability, so we have relatively little flux. If we have higher permeability, we have more flux. But in this case, it's negative flux, which means it's flux from the underside of the ice into the sedimentary basin as the ice sheet is growing. But then as the ice sheet starts decaying, roughly sort of 10,000 years ago or thereabouts, the groundwater flow direction reversed, and we now have water volume flux coming back towards the ice sheet base, just like it did in my conceptual slide that I showed you a little bit earlier on. And so the amazing thing now is, and this is what I mentioned earlier about the North American sedimentary basins, is that we can have thousands of years, or potentially more than thousands of years, time lag between forcing and response. So you're pushing water deep into the sedimentary basins, then when the ice sheet is advancing, then the ice sheet starts retreating, and then the water slowly starts coming back up again. So we can potentially force Antarctic ice flow, for example, in the current time, with water that the ice sheet pushed into the sedimentary basins 10,000 years ago, say. And so, that is a fantastic thought. It could do that, and it's not something that anyone is really taking into account at the moment. And then along with the water is relatively warm compared to ice. And so if you have water flux going towards the ice sheet base, you're also able to transport a lot of water, of heat actually, to the ice sheet base along with the water itself. And this is what I'll talk about towards the end of this time a little bit in a little bit more detail. Okay, and the other thing happens is, so we get isostatic rebound, which is basically, when the ice sheets shrink. So when the ice sheets grow, I should say, because you have extra mass building up, it will start pushing the crust and the ice mantle downwards. So they will very slowly start flowing out of the way, simply because of the extra weight of the ice. But then when the ice is shrinking, the crust and the mantle will start relaxing, will start going back up again. And if you have a really wet crust, that is more conditioned for rebound, so this moving back up again, than a very rigid, very cold crust would be, for example, or sedimentary basin underneath it. And so this is a possible nightmare for ice sheet models to take into account, should it turn out this really does matter a lot. Okay, and my last couple of slides before Chloe takes over then is the question of, okay, all well and good, so say, let's accept for a minute this is actually happening, but how do we actually go about measuring this now? So what do we need to do in practice if we want to go to the Antarctic and actually go and measure this? So here's the example from Pine Island Glacier, which was in the Amundsen Sea Basin. So Atsu Muto, one of our colleagues in our Thwaites project that Chloe and I are both going to work on, that did some fantastic work on Pine Island before. So you can see the ice sheet here. It's grounded on about 400 meter thick sedimentary rock with a till layer in between. And then there's some sort of igneous and metamorphic rocks underneath it. And then you can see here's an ice shelf, which is floating on the ocean water, which is a dark blue bit. And you can see the depth is in meters here and distance in kilometers in the horizontal, just to give you a sense of scale. And so the sort of things that we would typically do is we would, mount a radar on an aircraft, like a Twin Otter aircraft, for example, or a Basler aircraft, and we can measure the ice thickness, and we can also say something about how warm the ice is on the inside, and we can also say whether the base of the ice is wet or whether it's dry by analyzing our radar signals and how reflective they are basically as they come. So the aircraft will send the signal through the ice, it will bounce off the base of the ice or any layers inside the ice itself, bounce back up to the aircraft, and then we can analyze the signals and say quite a lot about what's happening inside the ice or at the base of the ice. We can't say too much about the actual base of the ice or the sediments underneath with the radar. It's quite limited in that regard. And for this situation, we need seismics. So we can do some seismic reflection work, and we can detect, delineate till layers, and we can also characterize those till layers, so we can say whether the till is wet or dry and whether the till is deforming and therefore allows fast ice flow or not. So there's quite a lot that we can do with this. And we can also investigate the deeper sediments. Here, so in this case, they're 400 meters thick, but they can be kilometers thick as well as sedimentary rock. And so we can do, we can mount a gravimeter or a magnetic instrument on our aircraft, and we can also deploy passive seismic stations on the ice. And if we take all those together, then we can say quite a lot about the internal architecture of those sedimentary basins and their thickness themselves. So those are all things that people have done in the past and that we're reasonably good at doing. But what we don't know is whether there's water in the sedimentary rock. So the bits, actually the critical bit for us, the question of whether there's groundwater sitting in the sediments, and or if the water is liquid, or if the water is frozen, or therefore makes permafrost effectively. Those are all big questions. And in order to answer those, we need electromagnetic geophysical techniques. And this is something that we've only very, very recently started cottoning onto. And this is what Chloe will introduce to you in a minute. So if we want to figure out, is there liquid groundwater, we need electromagnetic geophysical techniques. And then we can combine them with all the other things that we normally do, and then do a joint inversion ideally, or at least a joint interpretation of those data to tell us something about groundwater and also geothermal heat flux, which I'll, like I said, I'll hopefully pick up at the end in a little bit more detail. Okay, so my last slide for now is this one, just to say there's been a fantastic airborne electromagnetic survey using a helicopter a few years ago in West Antarctica and along the dry valley. So this is a part of West Antarctica where there's very little ice. So there's a lot of dry rock basically exposed at the surface, very frozen rock. But there's a few glaciers that are sitting on top of this. So you can see a profile here from the Canada Glacier, which is this one there. McMurdo Sound is over here. McMurdo Sound's there. But this also went further to the left of the image here, over some other glaciers and onto the Big Tailor Glacier here. And there's some frozen lakes in between, like this one, which is this lake here. And the interesting thing is, when we now send out an electromagnetic wave into the ground and receive the ground response to it, we can convert this to something called resistivity, which tells us how well electrical current can flow in the subsurface. Chloe's going to say a few more words about this. And basically, if the resistivity is low, it means there's liquid water here. If the resistivity is really high, that water is either frozen or is not present at all. And the really amazing discovery was that based on these helicopter-based electromagnetic surveys, colleagues realized there's a lot of liquid water actually in the subsurface that is several hundred meters thick, which are all these blue units here. It's really, really highly electrically conductive groundwater actually sitting below a very, very frozen surface here at the surface, as it were. And so this works really well, this system, but only if the ice is a lot less thick than 1 kilometer. Now, in most of Antarctica, the ice is, even the ice streams, the ice is usually around about 2 kilometers thick, between 1 and 2 kilometers, sometimes a little bit more. And in East Antarctica, the ice is up to 4.7 kilometers thick, which is pretty thick ice. And therefore, we can't use these active source EM systems there. We need to do something more clever. And this is basically what Chloe is doing. And so with this, I'll hand over to Chloe, but I'll have a look to see whether there's any questions that have come in the meantime. So I'm just going to stop sharing my screen and I'll see whether I can answer any questions if there are any. And in the meantime, Chloe can maybe get ready to get her talk up. Okay.
Yeah,
so
I'll just put up my slides.
So there's no question at this point. So be encouraged to ask questions. Chloe and I both very, very happy to answer those. So anything on your mind, just fire away using the Q&A function. Okay, I guess you might as well crack on, Chloe.
Okay, Bernd, do you see just one slide for me?
I do, yes, yeah. Just so I see
okay. Great. Hi, everyone. I am Chloe, as was mentioned earlier. And thank you, Bernd, for setting up my part of the talk so nicely. So Bernd just was telling us how electromagnetic methods are sensitive to electrical resistivity, and I just wanted to expand a little bit more on that and why that's so useful for looking at groundwater, particularly in an Antarctic or sub-ice sheet setting. So this plot shows electrical resistivity, which is an Earth property that actually spans several orders of magnitude. So we have electrical resistivity on the x-axis, and this is actually in log 10 scale, and conductivity is just the reciprocal, it's on the top x-axis. And here I just have a sample of Earth materials and their corresponding electrical resistivities. So we're looking at like 5 orders of magnitude here, which is very useful from a sensitivity standpoint. And for water in particular, we're looking at almost 3 orders of magnitude variation. And this is primarily a function of ion concentration. So as you have more dissolved solids in the water, it becomes more conductive. So like seawater is very salty, that would conduct electricity better than fresh water, which we would consider more resistive. And this idea will become important a little bit later on. So when we're looking at this subglacial groundwater environment, we're pretty much concerned with water and sediments, and the variation in sediment resistivity is also tightly linked to the water that is contained within the sediment pore spaces. And of course, we're also looking at ice, and ice is very resistive. And from a sensitivity standpoint, this is pretty useful. The ice is going to have a much different signature than the underlying water and sediments. And so like what Bernd just showed us, airborne electromagnetic techniques via this helicopter system produce these really beautiful images in the McMurdo dry valleys, where we saw this really salty groundwater system. But also, like what Bernd pointed out, this system really only works when the ice isn't very thick. And I chose the sort of cutoff at 500 meters. So here's a map of Antarctica just showing ice thickness, where the color scale actually saturates at 500 meters. So you can see while this system is really effective, this helicopter system for mapping groundwater, it's not going to work for most of the continent. So we really need something else. And this is where magnetotellurics, or MT, comes in. So this is a passive electromagnetic geophysical method. So passive means that our source is naturally generated. And here our source comes from either lightning strikes that are resonating throughout the ionospheric cavity of the Earth, or from solar winds interacting with the Earth's magnetic field. So this source, once it finally reaches Earth's surface, penetrates down through the ice and into the underlying geology, and then it will induce secondary electric and magnetic fields in the subsurface based on the conductivity variations in the sediments and the water and the bedrock, which we saw previously can vary quite a bit based on water content. And so this idea is really similar to what we have learned in like our intro physics classes, where we have a magnet and we move that magnet through a loop of wire. And we can see on this little voltmeter that a secondary current is actually produced by moving this magnet. So when we move back to this figure, the analogy, I guess, is that our source field is the magnet, the Earth is like this loop of wire, and we can see the secondary fields being generated with this little voltmeter. So in reality, we measure these fields with magnetometers and electrodes that we bury on the snow surface. And this is what that actually looks like in the field. So here we have this central hub that has our data logger. And then from there, we spread out and bury our magnetometers and our electrodes. And here's just a nice little time lapse of what it looks like to set up one of these stations. With a team of 4, it takes about 30 minutes to set one of these up. And that's if you have nice weather like we did today. If it's really windy or if equipment isn't working, it can take a bit longer. So this method is capable of sensing through this really deep ice, but you can see it takes a lot longer to set up just one of these stations than it would to fly a helicopter. So there are some trade-offs there. And this slide is really just to demonstrate the process that we go through to actually say something about groundwater. You don't have to understand all the nuts and bolts, but it'll give you sort of an appreciation of what we have to do with our data after we collect it. So first we have our raw time series of magnetic and electric fields, and then we do some time series analysis and convert these to what we call response functions, and we do that for each station that we collect, and these sort of start to give us an understanding of how resistivity is varying throughout the Earth. But the really big step here is taking our response functions for each station, so each one of these triangles, and then doing a geophysical inversion, so converting these into some sort of 2D cross-section of the Earth's resistivity. And really, we can start to say some things about groundwater when we look at an image like this based on the colors, which are resistivity. Oops. But what we can do besides just looking at these conductivities and making qualitative estimates, we can really do the next step and take this model and turn it into some sort of Earth property using a petrophysical relationship. So for this talk, we're going to be looking at how we take these images and move to salinity. So like what Bernd mentioned, I'll share some of our magnetotelluric data that I collected for my PhD. And this is work that I did with my advisor, Carrie Key, and also Matt Siegfried and Helen Fricker. So we went to the top of the Ross Ice Shelf here in Antarctica in this region called the Whillans Ice Plain. So we have these two fast flowing ice streams converging here, and they are underlain by a lot of subglacial lakes. And like what Bernd had mentioned before, these lakes are particularly interesting targets for groundwater because they could be these sort of focal points of where groundwater might be introduced into the sub-ice sheet environment. So I have squared the two locations where we did surveys. So we went to this lake called Whillans Subglacial Lake, and people like to abbreviate it SLW. And then we also went to the grounding zone where we think this lake actually drains into the ocean. So conceptually, this is what we are looking at. We did a survey at a lake that's buried beneath the ice. And then we went further downstream where the ice actually transitions from being grounded to floating. That's this marked by this black line on the map. And we also did a survey in this sort of region. So I will just start with our lake survey. The yellow triangles here note where we collected magnetotelluric stations. And I've just noticed the ice thickness here is about 800 meters. And our stations are spaced about 2 kilometers apart. So it took us about 2 weeks to collect all 27 of these stations. And this is just to give you an idea of what the data, the response functions look like for these circled stations. And basically what we have here is we have apparent resistivity on the y-axis and period on the x-axis. And on for the period, the smaller values correspond to shallower depths, and the deeper value, or the longer periods correspond to deeper depths of sensitivity. So really like this data, we're sensing the ice, and then this data, we're sensing the geology. And really here, I'm just wanting to show that as we look at our data, before we even invert it, we can see that there is variation as we go over the lake. But what's most interesting is turning those response functions into a resistivity image. So here we're looking at the top 5 kilometers beneath the ice surface, and we're spanning about 15 kilometers on the x-axis. And here the two main features are we have this blue region, which is representative of conductive sediments, and this yellow region, which is representative of more resistive bedrock. So with regards to groundwater, this blue region is the sediments that are really capable of holding that groundwater. Oh, and I should note the color scale here is log resistivity. So we have the more conductive values are in blue. And so this is just to really highlight those features. Within this blue region, I am dividing it sort of into two conductors, C1 and C2. And what's interesting about this C2 region is that it is actually so conductive that it requires the presence of salty groundwater. There's lots of things that can explain high conductivity, but in this case, we're pretty sure that there has to be some component of salty groundwater creating this high conductive region. And the sediments here, just to give you an idea, are about 1.4 kilometers thick to 5 kilometers thick. So now we can look at all of our resistivity inversion images that we created across the lake. And we see some trends like the sediments are thinning as we go downstream and then also across the lake. But really the main takeaway is that with our survey, we're seeing that there are extensive thick sediments beneath this lake, and they contain salty groundwater in this sort of dark banded region. So now what we're going to do is take this sort of image and actually convert it to groundwater salinity. And to do that, I use Archie's law, which is our petrophysical relationship. So Archie's law relates bulk resistivity, which is this image we have, to fluid resistivity and salinity, which is what we're interested in, to porosity and some cementation exponent. So we don't have any deep subglacial drilling cores, so we are going to rely on porosity from offshore Antarctica, where we do have deep cores. So here I'm just showing some porosity measurements in black from about 1,000 kilometers away. But we think the sediments there are relatively similar to what we're observing in this image, and we just fit some sort of decay fit, and this is the porosity that we're going to use to convert to salinity. And then for this n value, we know that for sedimentary rocks, there's this sort of typical range. So like I mentioned before, the blue region is really our sediment region, so that this is where I'm going to do the conversion from resistivity to groundwater salinity. So that's that same region we've been looking at from below the lake, and now the color scale is salinity. It's log 10 salinity, and it is a unitless value, but it's really similar to parts per thousand. And just to give you a better sense for what the values mean, I have pointed out where the water turns saline, which is this black contour, and then where the water turns to that of seawater, and that's noted by the red contour. And so each one of these panels is using our different M values, that cementation exponent. So even though, depending on how we decide to parameterize the model, we get these slightly different salinity distributions, overall what we're seeing is that the water does get saltier with depth, and we do have this vast reservoir of water that's underlying Lake Whillans. And at this star point, I'll actually just pull out these 1D profiles of salinity just as another way of looking at these variations. And we just have those for each of the 3M exponents. And also at this star, there are sediments and pore waters that were collected below the lake. They were able to get about 40 centimeters of sediments beneath the lake. And from those sediments, it was actually estimated that there was a more concentrated solute source at depth. So from this really shallow measurement, they predicted there would be something deeper down. And so with our magnetotelluric imaging, we were able to confirm that there was indeed this sort of deeper solute source at depth. So conceptually, this is what that looks like. Here's our lake, and where our magnetotellurics really adds to the story is the sediments and the bedrock. So we can see we have this really thick layer of sediments that's on the order of 1 kilometer thick, and the water within these sediments is increasing in salinity with depth. And so the fresher water up top might be from basal melt that's currently being in place or transported from elsewhere in the ice sheet. But this salinity with depth requires a different explanation, and I will touch on that at the end of the talk. But I did just want to hop over to our survey at the grounding zone. So I am just going to jump right to the resistivity images. We collected 2 profiles shown by these yellow triangles, and I'm using the exact same color scale here. So we can see overall we have a very similar system at this grounding zone. And I'll note that this black line, again, notes the transition from where there's no ocean water under the ice to where there actually is ocean water under the ice. Oh, there we go. Okay, so I'll pull out just a salinity 1D profile from a region that does have ocean water underneath. And we see again the sort of same trend where we have fresher water up top and saltier water near the base. So this is really interesting because we would expect that sediments that have ocean water overlaying them would actually be the salinity of seawater here shown in red, but we see those near surface sediments are actually a bit fresher, which was pretty intriguing. So this is the conceptual model of our grounding zone. We have water flowing in from further upstream where it eventually meets the ocean, and sort of the same situation that we saw beneath Lake Willans. We have some basal melt infiltrating the top layer of sediments, but as we get deeper down, we see an increase in salinity. And the fact that we saw fresher water beneath ocean water within the sediments indicates that there might be some sort of groundwater flow that's delivering water here, or it could be remnant melt from a time when the ice sheet was actually bigger. So just putting this into the context of this whole ice stream, ice plain region, here are 2 conceptual models, and they look really similar. So basically the 2 surveys that we did, we think are representative of this sort of larger system where we have really thick, extensive sediments that exist throughout this whole region, and they are full of groundwater that get more salty with depth. And I just wanted to briefly touch on the volume before I hand it off to Bernd. So if we do some volume estimates, just beneath the lake, we are estimating there could be about 20 cubic kilometers of water, which is 40 times the amount of water that's contained in this lake. For the ice plain, if we extrapolate to this whole region, we're looking at 6,000 cubic kilometers of water. And if we really extrapolate to all of Antarctica, we're looking at about 1 million cubic kilometers of water, which is 100 times the volume of all of Antarctica's subglacial lakes. So this is just pointing to the fact that there's probably this huge reservoir of water that really hasn't been accounted for yet. And at the risk of comparing apples and oranges, the continental wide basal melt rate is 65 cubic kilometers per year. So this is a rate, this is a volume, they're not exactly the same, but it kind of gives you an idea of just how vast this reservoir is compared to this melt rate, which is what currently goes into ice sheet subglacial models. And with the salinity, this is really interesting to me. I think the most plausible scenario is that we actually had a marine incursion. So here's our modern situation. But during the mid-Holocene, about like 7,000 years ago, perhaps, the ocean water actually came in a lot further and made these sediments salty. So I think that our data could not only tell us about groundwater, but could perhaps tell us about past ice sheet conditions and how far the ocean may have come inland in the past. And I'll just leave with these takeaways that we can use magnetotellurics to image these groundwater systems. We have this really large source of subglacial groundwater in Antarctica, and the salinity of it can provide insights into the past. So I can hand it back to Bernd now.
Okay, thank you, Chloe. So before I show my final couple of slides, I think there was a couple of questions. There was one on the chat about asking about satellite gravity, the gravity recovery and climate experiment GRACE. And indeed, that's a very important source of information on estimating mass loss or mass gain in Antarctica. And so there's a lot of experiments going on where colleagues are comparing satellite data in order to figure out whether or where the ice sheet is actually gaining or losing mass. And GRACE, because it's a gravity measurement, so directly effectively weighs the ice, is actually a very important source of information. If you're interested, there's a group called IMBIE, IMBIE, which is basically a satellite data integrated group that are basically looking at this, and they have a number of Nature and Science papers that are actually comparing those estimates with each other. So that's definitely being taken into account. But what that means for groundwater storage is completely unknown, and whether it's going to be useful or not, I guess we need to figure that out in the future. And then there's a second in the Q&A, there's a couple of questions about geothermal heating and why it's not been looked at very much recently, and that's a very good question again. So there was a horizon scan by the Scientific Committee on Antarctic Research in 2014, and they've basically pointed out that geothermal heat flux underneath the ice sheets is one of the biggest unknowns that we really need to get a handle on, and then include in our ice sheet models. And the difficulty obviously is that you have the ice sitting on top of the crust, and it's really, really hard to try and measure the geothermal heat flux. You can do this in boreholes, but drilling a borehole through anything more than a few hundred meters of ice is actually extremely difficult. And therefore the number of measurements are very, very few. And this is pretty much exactly why, what I'm hopefully going to show you now might inspire some thinking. And that's just basically adding to the fantastic petrophysical analysis that Chloe has just looked at. So if I just go back to my slides and pick up where I left off, which is here. I don't know, so I'm going to ignore these. It's exactly this question is, because it's so hard to measure geothermal heat flux, we know so little about it. Is there any way that we can use magnetotelluric data now to tell us a bit more about geothermal heat flux in those sedimentary basins underneath the ice at least? And the background to this, actually, just adding to what I've said a minute ago, this was nicely summarized if you're interested in a paper by Lösing et al., which I think I've cited down here. So all my everything I'm relating to is cited down here. So if you're interested, you can look back on the recording and hopefully pick up on these papers. Is there actually, there's been a few reconstructions of geothermal heat flux underneath the ice sheet. One in 2005 here using magnetics, then one in 2015, 10 years later, using passive seismic data. And then there was another one in 2017 using airborne satellite and airborne magnetic data. And as you can see, these all look pretty different to each other. So if you really want, there's some similarity maybe between this magnetic image and this one, but you have lots of heat flow, for example, geothermal heat flux here in Antarctic Peninsula in this one, and hardly any at all here. And likewise down here, McMurdo Sound and so forth, hardly anything going on down in here. but a lot more over here. So there are a lot of subtle differences. And seismic certainly seems to suggest we have an awful lot less geothermal heat flux than magnetic data. So there's very clearly something that we need to do here, because the uncertainty is huge. And in fact, Lösing et al. Have basically shown that using sparse data and using those sparse data to feed models actually can result in answers that are basically worse than not having those answers at all. So we're actually guessing might be a better way forward than actually trying to use the sparse data that we have available, because they make the guesswork even worse than it would be even without this data. So there's very clearly a big job that we need to do here. And one of the questions is, can we use magnetotellurics, for example, to help us with this? So again, if we just go back to our East Antarctic sedimentary basins, which are sort of somewhere over here, these are the ones I was talking about earlier. Brad Gooch has done some modeling on this. And so here we have the elevation from the base of the ice in meters, minus 400 meters. And here's the vertical heat flux in milliwatts per square meter. The average on the Earth is so around about 60 plus minus. So that's in the middle region here. And so if we allow for a lot of groundwater volume flux and some radiogenic heat production in the crust, then we can actually get quite a lot of vertical heat flux, like way above the average towards the ice sheet base. So depending on whether we have a growing ice sheet or whether we have a retreating ice sheet, we get one or the other situation here. These are quite extreme situations where we have quite a lot of groundwater flux one way up or down. And likewise for the radiogenic heat production. But if we go for more reasonable scenarios in between, then we can see we basically get situations that sort of sit somewhere around the average geothermal heat flux that we have on the Earth, and might have, underneath the Antarctic ice sheet, which is sort of around about 60 milliwatts per square meter. But the question is, can we actually, so that's the simple modeling, or quite involved modeling, I should say, but it's pretty much guesswork without measurements. And the question is, can we make better measurements than what we have over here? And so if we look at this conceptually, then if we have a material that's below 200 degrees Celsius, roughly, there's roughly a linear relationship between the bulk resistivity, so that those are the images that Chloe was showing us, and temperature. And the higher the temperature is, the more excited effectively the ions in the groundwater will get, and the more they will start moving around. It's a bit like, when you're starting to boil water in a pot on your stove, as it starts getting hot, the ions in the water get really excited and eventually end up with a convection current basically in your pot of water, or when you're heating up soup, that will also start convecting. And we can imagine something very similar happening basically in the groundwater reservoir, as you have geothermal heat flux coming up from underneath, touching the bottom of the sedimentary basin, and then basically diffusing upwards towards the ice sheet base through the sedimentary basin. And we can do some interesting analysis on this now, where we can try and convert our resistivity to temperature and then vertical heat flux using Fourier's law. I've got a paper on this, so if you're interested, you can look up the basic physics behind this. I won't go into detail, but we can basically show that if you have a situation like this, so this is Thwaites Glacier in West Antarctica, it's one of the biggest sources of worry that we have at the moment. It's a giant area, it's potentially really unstable, and there's some ideas basically out there that say that irreversible ice sheet retreat has already started at Thwaites Glacier. And this is why we have a massive NERC and NSF funded project there now to try and figure out whether this is true or not. Excuse me. And there's been some reconstructions from airborne radar data looking at the wetness of the base of the ice, and then doing some water modeling, hydrological modeling on this. And then so Dusty Schroeder has basically produced this map here, where there seems to be an average geothermal heat flux of around about 114 milliwatts per square meter from that model. And in parts, the really red areas is more than 200 milliwatts per square meter. So that's way, way, way above the average of about 60 milliwatts per square meter, potentially underneath the Thwaites Glacier. And we know certainly in the past, in geological history, there has been a lot of geothermal and volcanic activity happening there. There's some ideas that there might have been a subduction zone previously there in this area, generating a lot of this geothermal heat flux that we still see now. And the question is, can we measure this in some way? And so if I apply now my sort of resistivity, temperature, and heat flux model from Fourier's law to these data here, then I can reconstruct the bulk resistivity ratio that we should have between the top and the base of the sedimentary basin, depending on how thick the basin is. And on the right side here, you can see the temperature at the base of the sediment. And so for the sort of average heat flux, you can see if we have a 5 kilometer thick sedimentary basin, we have a temperature of about 200 degrees Celsius roughly. And if we have a 5 kilometer thick basin, but a 200 milliwatt per square meter a geothermal heat flux, then the temperature is much, much higher at the base of the sedimentary basin here. And the interesting thing is that the resistivity now between the top and the base of the sedimentary basin for those two situations, so in blue, 114, and black, 200 milliwatts per square meter, don't look too similar to each other, but we can show that very, very rapidly we get quite a substantial change in resistivity here, depending on the thickness of the sedimentary basin for those simulated geothermal heat fluxes. So for example, for a typical Antarctic sedimentary basin thickness of 2.5 kilometers, like we assume at the moment we have underneath the Institute ice stream, for example. We also know that some Cyprus coast ice streams might also have sedimentary basins roughly this thick. We get a bulk resistivity ratio of about 0.2. So effectively, this means that the resistivity should be five times higher at the base of the sedimentary basin than it would be near the ice sheet base. And therefore, if we considered our bulk resistivity images of the sedimentary basins, we should be able to say quite a lot about potentially the geothermal heat flux from the base of the sedimentary basin towards the ice sheet base. But obviously, as Chloe has outlined, we also have the salinity problem. So we have an overlapping heat flux and salinity change. And so we need to figure out how we can combine our magnetotellurics with gravity measurements, magnetic measurements, and seismic measurements in order to reduce basically the ambivalence that we otherwise get if we only look at one technique on its own. And we've seen this in our magnetic data and our seismic data, that where the geothermal heat flux really disagrees with each other. And hopefully, if we can add this magnetotelluric information to that, we can get a much, much better model out going forwards in the next few years. And then my last couple of slides. So this was all about the water itself, the temperature, and the salinity. But what about the structure of those sedimentary basins? And the Alfred Wegener Institute, which is the big polar institute in Germany, have developed vibro-size technology. I don't have time to talk about this now, but it can basically sound several kilometers down into the Earth's crust, even beneath the ice. They've got some fantastic images from East Antarctica. So in this case, the extreme ice shelf, which is an ocean underneath, looking into the sediments underneath the ocean here. They've also got some fantastic data where we don't have an ice shelf, where we're actually on the ice sheet itself, where it's grounded on the base, where we can really resolve very detailed layering in sedimentary basins. So hopefully we'll be able to see where the aquifer layers are and where the aquitart layers are in those sedimentary basins using this information here. And there's also been some work in the past where colleagues have used seismics to image tunnel valleys. So those are basically the sedimentary infills of where we used to have subglacial channels underneath the ice. So here you can see this is about 1 kilometer across the surface if you're 100 meters thick. And we get some very distinct seismic signatures in here that can tell us something about aquifers and aquitart layers themselves in those tunnel valleys here. And we've also got some data. So Peter mentioned at the beginning, I've done a lot of work in Greenland doing seismics. And we've detected a lot of sedimentary basins underneath the Greenland ice sheet. So there's one here, which is maybe 0.5 kilometer wide, underneath about 1 kilometer of ice above it. And the sediments themselves are about 100 meters thick in this particular example here. But, and this is basically just to remind me to say, don't forget about Greenland. There seems to be a lot of sediments in Greenland as well, not just Antarctica, and so groundwater might actually also play a big role in Greenland. So there's a huge amount of work that we need to do, and there's plenty of work to get on with in the next few years, to even sort of 10, 15, 20 years that will keep us quite busy. And I think with that, I say thank you very much for listening. And yeah, we're happy to take any further questions you might have. The more questions, the merrier. Thanks very much.
So Bernd, there's just a few questions in the chat, if you want to pick them up.
Yeah, so I think the first two were about the geothermal heat. Why geothermal heat flux was ignored so far, and that's, like I said, you know, it's because it's really hard to measure with the ice on top. But hopefully, as I've shown, we've got a potential geophysical way forward of answering those questions. Oh yeah, and then there's a third answer here. Yeah, it's about talking about observation and not the modeling. So ultimately, I guess we do need to combine the observations and the modeling together to get the right answer. But we know very, very little, so it's a very exciting area, and there's a lot of work to be done in integrating the geophysical measurements together with the models in order, hopefully, to get the right answers. Okay, I'm going to stop sharing, and I think, yeah, there's no more questions I can see, Peter. So I can probably hand over back to you.
Okay, well thank you very much, Bernd. I thought it was really interesting, and I mean, it's just astonishing. I mean, it wasn't so long ago that we thought of the Antarctic as this frozen ice sheet, frozen to the bedrock on the base, and actually all this really interesting information is coming out, particularly through geophysical surveys showing what a dynamic place it is with sediments sloshing around, seawater intruding, and it really is quite remarkable how our understanding, of this isolated continent has really changed in the last decade. So thank you very much, both Bernd and Chloe, for a really great talk. And sorry you're probably not here to hear a round of applause, but I'd like to thank the audience on their behalf for giving this, both giving this seminar. So thank you. Okay. I'd now just obviously like to say that with the conclusion of the seminar, there will actually be a Zoom social, so to speak. You've been given the link for this, so do please click on the link and have an opportunity to chat to each other, maybe chat to the presenters and everybody else. So hope to see you all in the Zoom chat in a few minutes. So thank you very much indeed.